Next up, we have the lead from Group 3, Evan Richard.
Hi, my name is Evan Richard, and I guess for the hat trick, today we're going to go and talk about commercial air conditioning. First of all, why does this matter? It's just because we live in South Louisiana, it's hot, and we want to make sure that our air conditioning systems are running as cleanly and efficiently as possible. So we're going to start off with some objectives. So what are the objectives of this experiment? So we want all the participants to become familiar with and understand the efficiency of the air handling unit, physical components of the system, as well as some of the variables in the air conditioning equations. So this is just kind of a basic air handling unit, as you've seen a couple times now. So just simply, you've got hot air entering your system, and it's going to pass over a couple of cooling coils, and you have cold air leaving, and then fans going to propel it out into your room or your car or wherever the system is. So these are some of the efficiency equations that you're going to see to kind of characterize the system. So the first one is going to be your coil bypass factor with some different temperatures of your system. And then the second equation is going to be your energy efficiency rating, and then finally the coefficient of performance, which we've seen before in our refrigerant charging effect experiment. One little phenomenon I just want to address real quick is overcooling, to where if you have a hot room on one side and a cold room on another side, and then you flip on your system, something that could happen is overcooling, which is kind of self-explanatory, is the room could be cooled more than you want, which you can make use of what are called VAV boxes. So this is kind of just a basic apparatus of our system, or part of it. Where it starts with an AC unit, a supply air fan, a supply air heater, which allows you to just to adjust the temperature of the air that's going to be entering your system. It's going to split off after hitting the VAV boxes into two chambers, which have different resistive properties, and thus could be characterized by different heat transfer effects. Those are going to simulate two kind of rooms, and we're going to analyze both those and take some temperatures and be able to characterize the system that way. So here come the thermodynamic equations that are going to allow us to characterize the system. You've all seen this equation before. It's the MCP delta T equation. One thing I found strange is this little 60 seconds over a minute conversion, which if you want your flow rate in cubic feet per minute, that should probably be the inverse, to where your output will be BTUs per second, which then you will be able to convert it to watts later. So the reporter for this experiment, what do you expect to get? So the first is we want the heat rate into each chamber. Second of all, we want to be able to plot temperature versus time in each chamber. And we want to plot something that's called the coil line. And then we want to determine the efficiency of the system by using two of the properties I described earlier, the energy efficiency rating and the coefficient of performance. Just some simulated results, just with some numbers I just kind of picked out. Just assuming a 200 cubic feet per minute flow rate, and then a room temperature of 75 and an output temperature of 60 degrees Fahrenheit. And then remembering again to flip that time conversion, and just we'll get a 0.9 BTUs per second, or about 952 watts. Just as in Kyle's presentation, safety is always important in any experiment that you do. These are just a couple of the safety concerns that we have for this experiment. You don't want to touch any of the ductwork components of the apparatus. They're going to be hot. You don't want to touch any of the installation during this experiment. You never want to turn on any of the heaters unless the fans are operating. You want to be aware that there's fire extinguisher just in case anything goes wrong. And then finally, stay clear of all electrical components, just for the same reason. We all want to be safe in these experiments.
So what's the difference between the two chambers in the experiment?
So the two different chambers are going to have different resistive properties, which are going to lead to different heat transfer coefficients, and so we'll be able to distinguish. We'll be able to analyze how the heat transfer